All right, well, we're going to move on to the part two of notes 2.4, which is looking at trig ratios and the coordinate plane with circles. So we're going to talk a little bit more about reference triangles, but in part one, we focused on looking at a point. So you had the coordinates of a point, and then you were able to create a reference triangle by drawing that perpendicular from the point always to the x-axis. So you're always going up or down to the x-axis, and then you created a right triangle. So you were able to look at theta and build the sides off of the coordinates of a point. Well, this time what we're going to do is we're going to really focus on the quadrant. So today's work is more looking at what quadrant are we landing in without necessarily knowing the coordinates of a point. So if we take a look at example one, I'm going to go ahead and get my coordinate plane all set. And we have a trig function sine, and the important thing here is that we're landing in quadrant 3. So if they didn't tell us that, we wouldn't really know what to do. So we're going to draw an angle, and it doesn't matter if the angle is positive or negative as long as you're landing, right now anyways, in quadrant 3. So if I draw this big angle somewhere, I don't know where. So I'm going to draw the terminal side. And remember, we're going to, so we don't know where that point exactly is, but we know we need to land down here in quadrant 3. So what I'm going to do is I'm going to draw a perpendicular to the x-axis, and we know our theta is always tucked in between the x-axis and your terminal side. So now if I use the information given, sine is opposite over hypotenuse. So this side would be -2. And our hypotenuse would be 3. So if we take what we know, we could have, I guess, already gotten the cosecant. Oh boy, sorry, which is -3/2. But in order to find the rest, we need this side right here, which I'm going to call x. So that means we're going to have to use that Pythagorean theorem again. So I think you all can handle this probably without me. But just so you know, you would want to set it up like this. So when it's all said and done, and you guys can do that on your own, you're going to get x is going to be radical 5. So this side is now radical 5. So when we go to do the cosine of this theta, we're going to do adjacent over the hypotenuse. Now, before I go on, I almost did this and I don't want you to do it. I'm going to go ahead and remind myself that we would go to the left of the origin. So I'm going to put that negative. I know it's kind of big to remind you that that needs to be negative radical 5. We went down, and that's how our angle is landing in quadrant 3. So our cosine is actually negative radical 5 over the hypotenuse. Now we're going to take the reciprocal, and once again you need to rationalize your denominator. So you should have negative 3 radical 5 over 5. Our tangent would be opposite over adjacent. So that would be a negative over a negative, which is a positive. And when I rationalize, I have 2 radical 5 over 5. And then our cotangent would be the reciprocal, which would just be, go away keyboard, radical 5 over 2. So it's really not that much different than what we did before. It's just you're not given the point. So just be very careful on whether you're going to the right or to the left of the x-axis, and be careful with your positive and your negative signs. Okay. So down here, this is just a review. Once again, I feel like the more we write it, the more you'll understand it. But remember, when you're looking at angles and you're trying to figure out the sine, we said in our last set of notes that the sine of theta always ended up being the y coordinate of a point over the radius. Our cosine was the x coordinate over the radius, and then our tangent was the y coordinate over x. But in a unit circle, we don't have to really worry about the radius because it's always 1. So in this case, we said that the sine would be y over 1, the cosine would be x over 1, and then the tangent is y over the x. So that's just a quick review from our first set of notes, okay? All right, let's go on. So what we're going to go on to now is what we refer to as reference angles. And we've already talked about reference triangles, but reference angles become important when we talk a little bit more, and you'll see this hopefully next week, but when we look at those special right triangles, we know that like 45, 30, 60, 90, all those become important. But before we get to that, we want to make sure you have a clear understanding of what a reference angle is. So if you look at this illustration right here, it's really showing you that when you have this blue angle with the initial side and then the terminal side, this angle specifically in this diagram anyways is landing in quadrant 2. So what happens is in order to draw that triangle, we keep saying you would drop a perpendicular. So the reference angle is going to help you not have to always know like the sine of anything bigger than 90 or the cosine of anything bigger than 90, because a reference angle is always going to be between 0 and 90. So even though you're going to be able to work with larger angles, we're going to have this reference angle. It's always going to be between 0 and 90, and it's always positive. So it's an acute angle formed by that terminal ray in the x-axis. And you're thinking, well, yeah, that's the angle we've been looking at a lot of. And you're exactly right. So what we're going to do, and you'll hear me call this at the very top of the page here, it talks about how the reference angle for theta is actually, it's an acute angle, and that's red theta prime. I don't get too picky about what you call it, as long as you understand how you're getting that angle measure, okay? So for example 2, we're going to find the reference angle of a negative 300 degree angle. So what I always like to have you do is, first of all, let's draw what a negative 380 degree, or negative 300 would look like. So here's our initial side, and we would rotate this counterclockwise to 300 degrees. So here is your negative 300 degree angle. So what happens is underneath here between the x-axis and the terminal side, this is called your reference angle, theta prime. And basically, if you think about it, if you went negative 300 degrees, this angle here to finish off that circle would be 60. Okay, so this is called your reference angle, and that would be 60 degrees. So if I write it up here officially, our reference angle is 60 degrees. So notice it's positive and it's between 0 and 90. Okay, so let's look at example 3. We have theta equals 150 degrees. So I'm going to, from my initial side, I'm going to rotate 150 degrees clockwise because it's positive. So here's theta. Theta is 150. So the angle that kind of gets you to the x-axis or under our triangle that we've kind of experimented with is right here. So this would be theta prime, we call it, and this angle would be 30 degrees. So the reference angle to 150 is 30 degrees. It's positive and it's between 0 and 90. Okay, so now once in radians, remember if it's given to you in radians, I want that reference angle back in radians. So 4 pi over 3. So you really need to start making sure you can do this in your head. But when you're thinking 4 pi over 3, I kind of think to myself, if I don't have this memorized, pi over 3, we need 4 of them. So if I think to myself what that means, pi over 3, I'm hoping you can do in your head, is 60 degrees, and then we need 4 60s. So if you're thinking, oh, I need to know what this is in degrees, that's 240 degrees. So we need 460 degrees. So if you walk yourself around the coordinate plane, okay, you're going to go clockwise to 240 degrees. So that would put me in quadrant 3. So if this is 4 pi over 3 radians, our reference angle, okay, remember it has to be between the terminal side and the x-axis. So it's going to be tucked here. And I know you're thinking, well, that's kind of inside 4 pi over 3. But this is your reference angle, all right? We don't care where we land, but the angle that would get us back to the x-axis. So if we went around 240 degrees, we want to get back to this 180. So that would be 60 degrees, right? Well, we know we want our answer in radians, and we just said earlier that 60 degrees is pi over 3. So the reference angle here for 4 pi over 3 is pi over 3. And for number 5, what we're going to do is we're going to take a look at 7 pi over 4. Once again, to do this in your head, I'm thinking pi over 4, I hope you have memorized, is 45 degrees, and I need 7 of them. So if we think of what that would be, 7 times 45 is 315 degree angle. So once again, I'm going to rotate 315 degrees to get me to where, this time I'm in quadrant 4. Now if I would think about what angle is going to collapse me back to the x-axis, that would be this angle right here. And theta prime, our reference angle, well, if that's 315, I need 45 degrees to get back. So your reference angle would be 45 degrees, but in radians, that's pi over 4. So once again, your reference angle. They are all positive, and they are always between 0 and 90. All right, let's go on, because I think you're going to see that this is going to go pretty quickly now. So if we go to the next page, the whole idea of trying to first start with points and knowing that they land in what quadrant is we got to now focus on our signs. So what happens is if you look at your reference angles, they can be in any quadrant, but the sign of whether, like if sine is positive or cosine, your final answer is positive or negative, depends on what quadrant you land in. So let's take a look at quadrant 1, okay? So what we have is we have kind of like a unit circle picture laid out, and we would know that this would be x and this would be y, and our radius would be 1. So we have our little right triangle set up for you. So if you know that the sine of theta, remember this is a unit circle, so our r would always be 1, so that's why you don't see y over 1 and x over 1. But notice that you're landing, the x value is positive and the y value is positive. So the sine would be a positive. The cosine would be x. Well, that coordinate's positive. And if you take a positive divided by a positive, you get a positive. So what's cool about this is that all trig functions will always be positive if you land in quadrant 1. Okay, let's go on. So let's look at quadrant 2. So if you look, I already have my diagram filled out. So we are landing in quadrant 2, so your x is negative and your y value is positive. So we have a negative and a positive y. So if you're doing the sine of theta, well, that's just y over 1, so that's positive. Cosine is adjacent, negative, x over 1, so that's negative. And a positive divided by a negative is a negative. So if you notice, out of your trig functions, sine, and then what we would have to look at, well, what else would be positive? Well, it would be its reciprocal. So don't forget about cosecant. So the reason it's not mentioned up here is because if a number is positive, then its reciprocal will also be positive. So let's look at quadrant 3. So we just talked about quadrant 2. Now in quadrant 3, we have a double negative whammy here. So when you take the sine, it's going to be, the result would be negative. The cosine would be negative, and then a negative over a negative and a positive. So if you look, the only trig function that is positive is tangent, and what would be its reciprocal, which would be cotangent. So that's all that's positive in quadrant 3. Now to the next page of your notes to finish off quadrant 4. So once again, I have the triangle set up. So we have x is positive, y is negative. So your sine is negative, your cosine is positive, and your tangent is negative. So in this last quadrant 4, we have cosine and its reciprocal, which is secant. So now you'll go on to the next video to wrap up our